Hello, and welcome to DevOps for C and C++. It keeps getting better. My name is Jerry Wiltse. I'm a Conan developer at JFrog. Please feel free to ask questions in the chat throughout this presentation, because I'll actually be available in the chat to interact with you while this recording plays. I have to say that I'm very excited to give this talk today because there are some amazing new and innovative features that can dramatically improve the use of Conan in CI pipelines. So let's get started. We'll introduce these new features in the context of the problems they solve. We'll first discuss the problems, then talk a little about the new features that aim to make things better, and finally explain how those features actually work. So let's start with a question. What's the biggest challenge in C and C++? I'll narrow the scope of that question a bit by adding, for professional development teams at large scales with multi-platform applications. Based on our feedback at Conan, one nomination has to be automated build and test. That's going to be the focus of our talk today, but we're not alone in this perspective. The keynote topic at CPPCon 2017 discussed this topic as well. It was titled Live at Head by Titus Winters from Google. That presentation was so relevant to our talk today, we're going to summarize some of the key points made there. First, changes to libraries which affect the code or the build of code can break consumers. The question, is this small change going to break some consumer downstream, is effectively unknowable in many situations. So in general, C and C++ devs have dealt with this by broadly recompiling and relinking after most changes. If this sounds like an old story, that's because it is. People have struggled to and talked about this for decades. I've given related talks in years past, and so have countless others. And there are a lot of reasons for why this problem has been so difficult to solve. And I've listed a few of them here. But unfortunately, the best advice from 25 years ago stands today. To be safe, rebuild your consumers after every change to a library. Other ecosystems have a de facto standard strategy for managing breaking changes. It's called semantic versioning, or semver. So why hasn't this solved our problems for C and C++? Well, actually, it has solved some of our cases fairly successfully. Semver has found purchase in a few aspects of C and C++. For example, virtually all major open source libraries release using semver. Many private enterprise code bases have also used it for internal components as well. So it does need to be considered and supported by tools such as Conan. But what's the essence of semver, and why does it fall short in some cases for C and C++? The theory behind semver is simple. Assuming you can organize your source code into discrete testable units, then you can build and test that code in separate CI jobs. And then your consumers can be updated to use newer versions of their dependencies when they're ready. That is, when someone takes the time to go and update and bump their versions as well. So this unlocks libraries to evolve at their own pace and avoid having to wait for all consumers to be updated. So that's good in many cases. If you think about it, that's really the only way an open source ecosystem can work. It works here because most open source projects have distinct teams that maintain them. And it's pretty difficult to imagine all the interconnected open source libraries in the world evolving together. So while it does work fairly well for this case, there are plenty of trade-offs. For example, some open source libraries are poorly maintained and some are abandoned. So maintainers may not update their project to use the latest versions of all their dependencies in a timely fashion, or some not at all. When a library is stuck on a very old version of another library, this can cause major problems for consumers. Also, some truly problematic releases of software, for example, security flaws in encryption libraries, they might stay in the wild forever. And so there are plenty of other trade-offs as well. At the same time, we can say that semver does not work in practice. Both statements are true. It all depends on context. So in the context of some video games, monolithic applications, and the large-scale code base at Google, semver is regarded as completely inadequate and useless. Why? What's so different about these contexts? Well, in these contexts, evolving everything together is the goal. Letting consuming code continue to use an old API or function is completely unacceptable. So, developing in this context has trade offs as well. For example, if a particular piece of code is delicate or extremely complex and calls into a library you're trying to evolve, it can be very difficult or dangerous to make any kinds of changes. It can also be difficult to test or prove something isn't broken somehow after a change you make. So, this kind of problem can actually slow down the development velocity of the entire project. Once again, there are many trade offs made in these kinds of development contexts. These are just a few. So, neither strategy is perfect. We just wanted to shed more light on why development teams really do have a legitimate need for non semver development scenarios. Earlier, we said that the end of the CI story for these cases was pretty sad. Generally, CI strategies resort to building their applications and their dependencies from source liberally to ensure correctness and compatibility. However, this is so painfully time consuming and inefficient that development teams have continued to look for more efficient solutions. In fact, this has been one of the things which has brought many developers to Conan in the first place. So, can Conan offer a CI strategy which provides equivalent compatibility guarantees to building from source, but without the extreme inefficiency and overhead? The answer is yes. In the past year, Conan and JFrog have invested significant research and development effort to address this use case. Of note, the features are very largely based on discussions with customer development teams trying to implement Conan into their CI. So, this is a good opportunity to mention just how valuable customer feedback is and just how dedicated the Conan team is to addressing that feedback. So, exactly how are things getting better? One major improvement in recent times is that the Conan team has a much better understanding of a few things than it did in the past. One very clear realization was what we talked about earlier. Semver is not a solution for all cases. This was a challenge for Conan because it was definitely developed with semver in mind. Another realization was that these teams still want the other benefits of using Conan even without semver. So during that same time, another realization occurred. Multiple problems and feature requests that different Conan users were reporting were all found to be facets of the same problem. First, Conan Center users were struggling with binaries being broken unexpectedly after rebuilds. Um, Also, enterprise users were asking about how to evolve open source packages they've brought in house, and they didn't want to change the version number, and they were looking for alternatives. But this made it clear that revisions are even relevant in conjunction with semver. So they're not mutually exclusive, but in fact, they're complementary at times. So finally, rather than continuing to consider the collection of problems out of scope, the Conan team decided to tackle it and give users a first class experience around it. So, from these advancements and understandings of CI use cases and challenges have come new features. The first feature is actually a new fundamental building block of the package model. It's an opt in feature, so all the related behaviors are off by default. But called revisions, they ensure that every time a recipe or binary is exported or built with a change, the new binary or recipe doesn't overwrite the old one, even if it has the same package ID. Instead, a new hash is produced and the new binary or recipe is stored in a new folder. So when I first learned about this feature, my immediate reaction was concern. Conan already creates so many binaries, and if it starts now storing and creating revisions of each binary, I didn't understand how one would ever configure a CI job to specify the correct versions and the correct revisions of each dependency in each binary. It seemed unapproachable to me. So it turns out that a related feature called lock files is the answer to these questions. The lock files feature works together with revisions to enable a complete CI strategy, which is free from semver. So without languages, while other languages have lock files, implementing them in C and C++ in Conan was very challenging. If you're not familiar with lock files, the general principle is simple to explain. At the start of a build, you can lock the entire dependency graph. Then you provide a Conan reference, either a path to a Conan file or just the full reference, along with a profile, and you get back a lock file named conan.lock. So features around these lock files are what make revisions usable in the CI workflows. For example, at the end of the build, we can use a lock file to generate a build order file. And from that build order file, we can see what packages need to build next and trigger the relevant CI jobs for those packages. So here's a sample lock file. Notice the full package reference with revisions at the bottom, labeled pref. It shows recipe version, recipe revision, package ID, and package revision all in a single string. This is considered a full package reference. So now that we've explained what revisions and lock files are, we can explain the fun part, how they can actually be used in CI workflows. So lock files are a bit challenging to think about at first, so let's start by clearly stating some requirements and constraints on our CI jobs. At a high level, the common requirement across most teams working with us on these features was something like the following. For every non-versioned library change, rebuild the library, then rebuild all the consumers of that library on all the supported platforms, even when there's multiple PRs coming in or multiple commits coming in at the same time. So to make that even more clear, the entire pipeline should run against each specific individual change in isolation separately, all once again without semver for controlling the version. So the control flow of this process doesn't actually seem that complicated at first. Every time there's a change, lock the graph, then rebuild the change component, generate a build order file from the lock, and then use the build order file to trigger downstream jobs. You just have to be sure to pass the original lock file to each job. When Conan gets a lock file, it updates it, recording which package was just rebuilt. So this is how the build order determines what needs to be built next. With this approach, we actually meet all the requirements and satisfy all the constraints we mentioned earlier. We're not relying on semver to address the new binaries. Any concurrent changes are isolated and built and tested properly by virtue of the lock files containing the full package reference, and everything is reproducible given the original lock file. So this sounds great, and it really is great. However, it's important to pause and give consideration to the implications of using lock files as the basis for your CI strategy. If you've implemented CI with Conan before, these lock files will certainly require you to change and rethink some of your assumptions. Also, you generally just can't add lock files to your existing build jobs and build strategies. You'll have to retool. To really understand how the lock files are designed to work, we have to talk about the difference between two different perspectives on our CI jobs. That is, starting nodes first versus ending nodes first. And by first, I don't mean first to build. So let's define those terms a little more clearly. These are not official mathematical terms. However, we did derive them based on some other terms which are official. So see, lock files are related to the field of mathematics known as graph theory. So let's quickly define some terms specific to that. The acronym DAG, pronounced DAG, stands for directed, as in one directional, acyclic, which means doesn't have any loops, and graph, which is a set of relationships. So the image on the right is a visual representation of a DAG of Conan packages. This can be generated for any recipe with the Conan info command. So the word node in graph theory would generally refer to the Conan packages in this DAG. The lines with the arrows in this image indicate which packages depend on which other packages. So the arrow represents depends on. So hopefully now we can more easily define the terms we used earlier. Our focus today is the case where the library changes and we want to build and test all our downstream consumers. So here we say that the starting node is the library that changed. In CI, that will kick off a job, which will lead to a chain of jobs, which eventually rebuild and retest all the consumers. We call the final consumers the ending nodes. So specifically, we're talking about those consumers which have no consumers of their own. That's what we call an ending node. So here's a sample of a build order file that was generated after a change to zlib. If you read the file from the top down, it makes the most sense. You would next need to rebuild OpenSSL and Boost. Once Boost and OpenSSL are done, then Poco could be rebuilt. Once Boost and Poco are both done, then we could rebuild our app, which is shown in the image as conanfile.txt. So in this graph, zlib is the starting node, and conan.file.txt would be the end node. When we say starting nodes first thinking, what we're describing is a habit of planning everything in your CI around the starting nodes. In our example case, that would be zlib. So if you know one of your products or multiple products depend on zlib, it's pretty intuitive to think this way. You think, I need to start by creating a CI job for zlib to build all my binaries for all my supported platforms. And then once that's done, I can set up a job to build all the packages which depend directly on zlib. And then work your way through creating CI jobs for each of the dependencies in order that way. It makes sense for a lot of reasons. If you use Jenkins, you might create a Jenkins file that looks like this. You can add a stage for each supported platform, assuming you know what all of those are at the start. This is how we did it in the open source packaging world. This is how the Conan team did it for Conan Center. So it's very intuitive and it's conventional. It's how most other languages set up their CI jobs. Unfortunately, this approach has largely unacceptable consequences, again, at scale. If you want all the jobs to use the right package IDs and the right binaries, you have to get everything right. Every profile name, every Conan option has to be correct in every Jenkins file. By correct, we mean consistent with every downstream job, including the end nodes. So it really and truly does not scale past a few hundred jobs. And even at that scale, it's already unmanageable. So furthermore, this approach doesn't give us any of the benefits that we want from revisions and lock files that we were talking about. So it's unacceptable on many fronts, and we don't recommend this strategy moving forward. Many teams implementing CI on Conan started with this strategy and have eventually come to us with the feedback that they have really struggled. So fortunately, there's now a new approach that we can try and we can recommend to solve this problem. So now we're going to try to plan a similar CI setup for the same application, but we're going to think about it in terms of the end node first, our application. It might seem less intuitive, but let's just try it out. So the following story is actually easy to relate to. We're developing an application locally. We know how to build it, including the options we want. We have a profile defined and we want to use it. So in theory, we just want our CI to do what Conan create with -- build all would do. But we want it in a more multi-job, multi-platform, parallelized way. Most developers are familiar with this situation. You get something to work locally, now you want to put it on CI to run. So fortunately, that familiar experience is very compatible with how lock files work. It turns out that lock files require us to approach the problem in this end node first way. Most people immediately get the general reasoning for lock files. They want to lock a dependency graph so that other changes don't affect the build that you want to run. But most people don't realize that this implies a very specific perspective for it to be useful. For example, if we do a graph lock on zlib's perspective, we actually accomplish nothing. It has no dependencies, so nothing will be locked. What we really mean to do is to lock all dependencies from the perspective of an end node in the DAG. Another thing that's important to realize is that lock files must contain all options for all of the packages in the DAG. So remember that options can affect what packages are included or excluded from the dependency graph. So they're actually part of the dependency graph calculation. So it's really important that we have all the settings and options relevant to all the packages when we do the lock. So interestingly, the profiles get embedded in the lock files, which also implies that we'll need to be able to define the list of builds to run dynamically in our CI files. This might be, for example, dynamic stages if you're using Jenkins, or other CI systems have similar constructs. But we'll talk about why this is in a moment. So our previous explanation about how lock files work in CI was a bit oversimplified. Let's add a little more detail regarding starting nodes and ending nodes now. At the start of any job which builds a node in the graph, whether it's zlib, OpenSSL, or Boost, we need the log files from all consuming end nodes to do the build properly. So we need to get all the end node log files in order to know the sum total of all the profiles we need to build at each node. So since we get that list during the job, and that list could change over time, this is where we need the dynamic builds for. This idea of dynamic builds in a CI job can be tricky, but the good news is that it actually solves some of the other problems we mentioned earlier. So consistency across many Jenkins files and scalability. The bad news for people with existing deployments of Conan in their CI is that you'd probably be required to do a significant refactor of the CI builds across your environment to implement lock files. As we said earlier, you can't just add lock files to existing jobs without retooling them. So after we have all the lock files for all consumers, we can rebuild our starting node and then begin triggering the downstream after downstream nodes until we reach the ending node. And remember that we pass the lock file to each job so that it can be updated properly. So in summary, this talk was a fire hose of information. I don't expect anyone here to fully understand how to implement lock files in their CI today. I've spent weeks working through the concepts with real environment scenarios, and it's very difficult. It's a complicated topic. However, my hope is that you now understand the spirit of these new features and how they may or may not be relevant to you in your Conan deployment. For organizations which need to be able to test changes without bumping versions, finally, we have a supporting mechanism. If they also need to be able to build multiple PRs at the same time, finally, we have a supporting mechanism for that too. So I'm out of time, but it's important to point out that the Conan team is still continuing to work and improve these features with every release. So stay tuned in the coming weeks and months for additional features relevant to Conan and DevOps for C and C++. So if you're exploring Conan and CI in a professional setting, we also want to suggest that you attend one of our CI/CD training sessions. We go through extensive exercises using revisions and lock files in realistic CI environments. And if you want information about this, please send an email to conandays@jfrog.com. In either case, we also encourage you to contact us very early on in your journey, whether you're doing a POC or an implementation. You can contact us via GitHub issues or the Conan channel in the CPP Lang Slack. Thank you very much for your time. Have a great day and enjoy the rest of Swamp Up 2020.